Hello, in this lesson, we're going to talk about solving complex trig inequalities. And in some situation, we need to solve these kind of inequalities. So by far, we have covered solving equations in inequalities of various kinds, including quadratic, exponential logarithm. And so now it's time to look at the complex trig inequalities. I have some homework for you there, so please take a look at the homework, and I'm going to pick some questions from the homework. You know, the general principles to solve these inequalities are very similar, right? We know that solving inequalities, the typical steps, the typical step we do when we solve inequalities is to make zero, make product, or make quotient. So that's the general step. Okay, the general idea. Okay, first is making zero, right? Secondly, make product or making quotient. By doing so, we get to use math principle number 5 and 6. Number 5 and number 6. Okay, so what are principle number 5 and number 6? Principle number 5 and number 6, right? Number 5 says if A times B equal to 0, then A is 0 or B is 0. Okay, for quotient, right? We also have a similar properties. I didn't list them in the general principle, but it's not hard to figure out. If that we have A divided by B equals to 0, then A must be 0, okay? And B cannot be 0, okay? And B cannot be 0, okay? B cannot be 0 is to ensure the domain. So this equals to 0 imply that B cannot be 0. Okay, so we should put it this way here, right? That in this statement, B cannot be 0. B cannot be 0. It should be put here. Okay, so when the quotient is 0, denominator cannot be 0, so numerator must be 0. Okay, principle number 6. It is about that positive number times positive number is equals to positive, right? And the positive number multiply negative number equals to negative number, right? And negative number times positive, negative times positive equals to negative. And the last, of course, is negative times negative is equals to positive. And for a quotient, the properties are similar, right? It's positive divided by positive is a positive. And positive divided by negative is negative. Negative divided by positive that's going to be negative. And last but not least, which is negative divided by negative, is positive. There. Okay, so all of our strategy to solve inequalities in, here, making zero, making product, or quotient in general. So, but in solving trig inequalities, we have to take into consideration the domain and range of these specific functions. So let's look at some let's look at some questions in our homework. Okay, let's take example number 1. Okay, so let's look at a question, the first one, right? The first one, which is sine x squared, sine square x is greater, sine square x minus 2, I believe, okay? So of course it's solving for x, Okay, the question is sine square of x minus 2 is larger than or equal to 0. Okay, to solve this inequality, and of course we already have 0 on the right-hand side, right? So algebraically, we know that we have a function, right? Flow-wise, from a function's perspective, this, we always have this function perspective here. We have a function, and this function, of course, is this guy, right? It produces an output, and we want the output to be positive or 0. Okay, that's what we want. And algebraically, we can work it out. You can do the graph. As well. Okay, we're gonna do graph just a little later. And we can add a 2 on both sides. And then we take square root on both sides. Okay, and then we got absolute value of sine x greater than or equal to √2. Okay, and then this fits the model of solving inequalities of absolute value, right? The absolute value of omega is greater than or equals to √2, right? And then, right, so this is an if statement, of course. Then omega would be less than or equals to negative √2, or omega would be greater than or equals to √2. Okay, so we have this model. And our omega, of course, is sine x, right? Okay, so here we get a sine x will be less than or equals to negative √2, or sine x is larger than or equal to √2, right? So these are the two models we get into. And so here we got 2 inequalities, okay? And then we're gonna solve for x from here. Okay. What do we get from the first one? Well, remember the range of sine. What does it say? What's the range of sine x? The range of sine x is that sine x is between +1 and -1 for any real number. For any real number. Okay, for any real number. So these will never happen. And these will never happen too. In fact, this will never happen, right? You could have stopped here. Therefore, at this point, we can say there's no solution. No solutions. Okay, no solutions. So even though we go by whatever we have done, the regular steps, but we also need to take into consideration of domain and range of these specific functions. Here is sine x, sine x. You can see all things are coming together, right? Inequality, sine x, absolute value. There's multiple functions involved. The other perspective is that you can look at the graph. You can look at the graph, okay? So to look at the graph of solving this inequality, and then you would like to graph sine square of x -2, right? So what does that picture look like? Okay, that's typically pretty difficult to graph, right? That's pretty difficult to graph. So we're going to just make some adjustment. Okay, let's go like this. It looks like it's periodic, right? It's periodic. And that's the function. And we want this function to be greater than or equal to 0. Greater than or equal to 0. Okay, you look at the curve. The curve is entirely, let me do. Okay, you can see the curve is entirely underneath the x-axis, right? All the output, right? All the output. So what are all the output? We want the output to be positive or 0, right? You can see all the output. This is the largest output for whatever input. And these output are what? Are negative. So no output is even close to 0, right? So that's how there's no solution. And we want the output to be positive or 0. And we see no output that is 0. And we see no output that is positive. So from the graph, it tells us that there's no solution. Okay, so no solutions either. Okay, so the graph will tell us if you know how to read the graph, right? Now we do. So now let's look at the second one, example number 2. And this is going to be the second example. Okay, so let's look at example number 2. Okay, so here we have a quotient situation. Okay, in this quotient situation, the inequality we're solving is going to be, it's like this. Okay, you probably see that. It's 1 plus sine x. Okay, so solve for x. Right? And we have a quotient situation. So 1 plus sine x over 1 minus sine x less than or equal to 0. Less than or equal to 0. Okay, so here we have to put on our thinking cap. Okay, besides knowing these mathematical principles, right? So we know these mathematical principles. So I'm going to put these mathematical principles right next to us for our reference, right? So these are mathematical principles. And of course, only quotient case apply to us, right? So these 4 cases. So let me make a kind of a table, right? So that way we can you know, move them about easily. Okay, so over here. So I want you to think about how shall we approach this question, right? We have the mathematical principles. Can we multiply both sides by the denominator, provided the denominator will not be 0? Can we do that? Okay, do you know what I meant? Okay, so I'm going to show you what I meant. Okay, what I meant here is, can we do this? Would we do this, right? I'm going to assume the denominator will not be 0, okay? So provided that the denominator will not be 0, we just guarantee that it's not equal to 0. Under this assumption, of course, we can determine the domain. Can we multiply both sides by the denominator? Can we multiply these on both sides? Can we multiply by this? Can we multiply this quantity on both sides? Can we? Can we? In our previous discussion, right? In our previous discussion, right? We once had a question like this. I think it was x plus 3, right? Wait. I remember something like that, right? X minus 3 minus x plus 3. I think this was a question. This was a question before. Okay, solving this inequality. Okay, so previously we solve for x, right? We have this inequality. It could be greater than, less than, equal to, whatever. I think it was less than equal to. Okay, let's change it to less than equals to. Suppose this is the inequality we're solving. At the time, we said if we multiply both sides by the denominator, right, provided the denominator is not 0, okay, we also provided that 3 minus x is not 0. Can we multiply that on both sides by 3 minus x? Can we multiply on both sides by a quantity that's not equal to 0? Can we do that? I want you to think about it. Maybe you would like to pause and think about it. All right, previously when we discussed how to solve this inequality, we said that if you multiply both sides by 3 minus x, knowing that 3 minus x cannot be 0, which implies that x cannot be positive 3, right? Under this assumption, right, we cannot multiply 3 minus x on both sides without any restriction, okay? The reason is that we don't know whether 3 minus x is positive or negative. If 3 minus x is positive, and this will be okay. But if 3 minus x will be negative, right? So if if 3 minus x is positive, right? And that will be okay. But if 3 minus x is negative, then this has to switch. We have to switch the direction of the inequality sign. Without knowing the sign of 3 minus x is positive or negative, then we would not know whether we should switch or not to switch. That's why we cannot do it. That's why we cannot multiply it without any additional information. Now, that was before. And of course, this principle is still holding true, right? This principle is still holding true. Now, for our situation, do we know the sign of 1 minus x? 1 minus sine x, okay? So first, let's start with determining to guarantee 1 minus x sine x is not equal to 0, right? So we first do the domain and then we come back for this discussion. Okay, so we determine the domain. The domain would be 1 minus sine x cannot be 0. That is that sine x cannot be 1, right? So what x cannot be, right? Sine pi over 2 equals to 1. Sine pi over 2 plus 2k pi equals to 1, right? So as long as x is not equal to pi over 2 plus 2k pi, right? Where k is integer, then we're fine. So that domain is determined. So in the domain, so we're gonna put the domain assumptions right here, right? So that piece is guaranteed. So we guaranteed. So in the domain, so in the domain, could we do the following? That means, do we know the sign of 1 minus sine x? Do we know the sign of 1 minus sine x? Okay, look at this. We know that negative x less than or equals to sine x less than or equals to positive 1, and this is always true for any real number x, right? So that's the range for sine x. If we take this piece, right? Then this is always true for any real number. This is true for any real number, right? And what does that mean? This means that if we subtract sine x on both sides, we'll have 0 less than or equals to 1 minus sine x. What does that mean? That means 1 minus sine x is always greater than or equal to 0. Since we guarantee it cannot be 0, right? So we have less than 0 in the domain, a less than 1 in the domain. In the domain of this quotient, right? Because we rule out the possibility for the equal to 0. So in the domain, this is true. So in the domain, this will be true. So 1 minus sine x is actually positive. If 1 minus sine x is a positive number, can we multiply this on both sides? The answer is yes. The answer is yes, because we know the sign of this multiplier, which is a positive. Okay? So yes, because 1 minus sine x is positive for x right? In the domain of the function, in the domain of the set function. Therefore, we can multiply that on both sides. Okay, so this is the, these are the additional answers. Does it contradict to what we said? No, it doesn't. It doesn't contradict with the principle, because if we know 3 minus x is positive, then we can multiply both sides by it. If we know 3 minus x is negative, we can multiply both sides by the number. You just have to switch the inequality sign. So it doesn't contradict with whatever the principle is. So that principle, which we recall, okay, recall the principle we have studied, that if A is larger than B, then, okay, A times C is larger than B times C, provided C is a positive. C is a positive. Okay, so it doesn't contradict. In this case, we have a less than equal to 0 case, so less than or equal to. So this will be less than or equal to. Okay, so it doesn't contradict with any principle, we can. So as a result of this, we got 0 times a positive number equals to 0. And on the left-hand side, these two multiplying this is reduced. So we have 1 plus sine x is less than equal to 0. Continue to solve this inequality. I will give you a version of how to show work, okay? Now, 1 plus sine x less than or equal to 0. What is the solution to that, right? So from here, we multiply both sides by 1 minus sine x, right? So we got here. If this is true, what will be the solution for sine x, right? So what we can do is that we can subtract 1 on both sides. X is less than or equal to -1, okay? We know that sine x is always between -1 and +1, okay? We know that sine x is always between -1 and +1 for any real number, right? For any real number, x. Of course, in our case, this is true in the domain of, right? So if we just take this part, okay, if we just take this part, which part? If we just take this part, that is true for any real number, right? Now, if we add, this is always true. So sine x less than equals to -1, and sine x is always greater than equals to -1. And for these both to be true, and there's only one choice, which is sine x equals to -1, right? This is always true. And this is if, this is what we wanted. Less than -1 is not possible. So we can only have sine x equals to -1. Okay, so what will be the solution to that? That solution would be x equals to 3 pi over 4. I'm sorry, 3 pi over 2 plus 2k pi, where k is being any integer. So this question sounds like rather complicated, but we really go around it with, not go around it, we just go about it using the domain and range analysis and using the basic principles of solving inequalities. Okay, so let me put together how to solve these inequalities and what can be, what is not necessary to show, and so on and so forth. Okay, so with this whole analysis, okay, so I'm going to give you a version of the work to be shown. Okay. I'm going to give you a version like that. Okay, so solve for x. Right here. Okay, so how do we show work? How do we show work? Let's see, 150%, I'm making it larger. Okay, so we start showing work. Okay, let's see. Okay, from here. Okay, so we have the show work part. Show work. Okay, so our question is solve for x. So first we determine the domain, right? Denominator cannot be 0. I'll make the font size just a little bit larger. Okay, so in the domain, okay, in the domain, we're going to do that. Okay, and here you can cite a reason. You can cite a reason saying 1 minus sine x, wait. 1 minus sine x is always positive. Okay, 1 minus sine x is always positive. Okay, equals to 0 is not going to happen because we're in the domain. We're discussing it in the domain. And now, right, so this is just to demonstrate it, right? Demonstrate how it is, right? You can just use that reason. So 1 minus sine x is positive. So we can remove all of these, right? And the next step, you can just multiply because we already multiplied. You just multiply by a positive number, right? In the domain, we have that. We have that. And then you can say, since this is true, right? So these two combined, we can say but, right? Because this is a half of that inequality for the range of sine. So if you want to have, if you want this to be true, and this is always true, right? There's no if, right? This is always true. Therefore, we can only have this. We can only have this. Go like this, okay? Because if this is true, then this is true. But sine x is greater than or equal to -1 all the time. Therefore, both conditions combined, both situations combined, we have sine x equals to -1. So as a result, x equals to 3 pi over 2 plus 2k pi. So that would be the solution. So that would be the solution. Okay, so we first determine the domain and we multiply both sides by a positive number, okay? Because inside the domain, this is always a positive, okay? Not equals to 1, right? And so if this is true, then multiply both sides is true. So this is true without changing the direction. And if this is true, then this is true. But this is always true, therefore we get this one. Okay, I hope I've made myself clear. If you have any questions, please don't hesitate to reach out to me. Okay, so now you may say, well, can we do by sign? Can we do by sine, right? Surely, you can do the sine analysis. You can do the sine analysis, right? The sine analysis here, if you look at the sine analysis, if you look at the sine analysis, you have to understand that you still have to mention the domain. You cannot get away with not talking about domain. So you always have to consider the domain, right? Once the domain requirement is satisfied, then you can talk about the sign. But the thing is that 1 plus sine x, right? As we said earlier. So the primary thing we did here is that you have sine equals, let's write it this way, okay? With this half, right? From this half of this inequality, you will get 0 less than equals to 1 plus sine x, right? So that's the numerator. So the numerator is always positive or 0. The denominator from this piece, right? From this other piece, right? We get 1 minus sine x is always greater than equal to 0, right? And of course, we want it to be in the domain, and this is going to be positive. Okay, this is going to be positive. In the domain, this is going to be positive. This is going to be positive. Okay, I would say in the domain. In the domain. Okay, so less than or equal become less than because it's domain requirement. So we have that. So in the domain, the numerator is always greater than or equal to 0, right? This is always greater than equal to 0. And the denominator is always positive. So for the numerator to be, so for the whole thing to be negative or 0, there's only one choice. There's only one choice because the numerator always is, this is always for all real number x. So what situation do we have? We have a situation that the numerator is always positive or 0, positive or 0. The denominator is always a positive. And we want this thing to be less than or equal to 0, right? So positive over positive is not going to make, it's going to be positive, right? So that's not going to make, only 0 over positive can make it equal to 0. That's why we ended up with the numerator has to be 0 to make it true, right? So that's how we get that solution if you do the sign analysis, okay? So in these situations of solving trig inequalities, you have to take a lot of factors into consideration besides using the principles, Okay, so let's look at another example, example number 3. Okay, example number 3. And once again, we solve for x, right? And here we have a cosine x over 2 plus sine x. And we want this product to be greater than or equal to 0. And the first thing first, of course, you're going to decide the domain, right? Domain will require 2 plus sine x should not be 0. Okay, well, sine x is never going to be larger than 1. So 2 plus sine x is always positive. Okay, so let's type it. Because for any real number x, for any real number x, right? Oops. For any real number x, sine x is always between -1 and +1. Therefore, 2 plus sine x is always a positive. So denominator will never be 0. So the domain is all real numbers. Domain is all real numbers, right? So here you can see we use the property and we use the range for sine x to make that domain determination for this function. Okay, so the denominator is always a positive. And we want the whole quotient form, right? We want the quotient form to be what? To be positive or 0, right? So we have a scenario that the denominator is always a positive. The numerator is cosine. And we want this to be greater than or equal to 0, right? So what will that lead us to? Of course, it's going to be cosine x is going to be greater than or equal to 0. You can multiply both sides by 2 plus sine x if you want, right? You can achieve this by doing that, or by sheer analysis, right? The denominators are always positive. For the quotient to be positive or 0, the numerator has to be positive or 0, right? So if you like, you can multiply both sides by the positive number, 2 plus sine x, which is positive, right? So either way, you get it. Now the question is, how do we solve cosine x greater than or equal to 0? How do we solve for that? Greater than or equal to 0. And this time the cosine curve will be very useful to give us that visual. Okay, of course, we can also look at the unit circle. Okay, we're gonna look at both. Cosine curve. Right, you can use Decimals picture. Right? We want a cosine to be positive or 0. So what are the pieces that are positive? That's a positive piece. That's a positive piece, right? That's a positive piece. All of these are negative pieces, right? All of these are negative pieces. And how about the crossing? We want it to be equal to 0, be fine. Okay, so what will be the solution? Well, these intervals will be solution, and these intervals will be solution, and these intervals will be solution. We have many, many intervals as solutions, right? So how do we describe these intervals? For example, can we describe this interval? What is that? That's from -π/2 to +π/2. Yeah, -π/2 to +π/2, inclusive. Okay, how about this interval? So you have to identify what that interval is, right? You have to identify that interval. So for this reason, I'm going to give you another convenient tool, which is Decimals. Okay, hold on. Okay, just 1 second. I'm going to bring that picture to you. Decimals. I typed the demos. Demos give me a different website. Okay. So I'm going to bring this Desmos in front of you. And we're going to share the screen. Okay. Cosine X. The convenient things about this this graph is that you can use it to identify points, okay? The same idea though, right? It just makes it easier to identify them. So this piece is a positive pieces, right? Positive pieces. You're familiar with the graphing, that will also help you. So you have this interval between negative pi over 2 to pi over 2, 3 pi over 2 to 5 pi over 2, negative 5 pi over 2 to 3 to negative 3 pi over 2. But remember, cosine is an even function. So if you can identify all the intervals on one side and the other interval on the other side, it can be identified easily. Okay, so without further ado, let's look at the unit circle. Let's look at the unit circle perspective. Okay, we have a unit circle that we can use, right? So I'm gonna find my unit circle. Ooh, where is my unit circle? Please show up. You guys go ahead, find your unit circle. There. I know I have it. It's just, I'm going to bring my unit circle. Unit circle oftentimes is very, very useful. So let's just go back to the picture here, right? So using these back to back, it could help us to identify the points easily, right? Because you can see when you look at the positive cosine value or zero cosine value, so this is 0, you just look at the red numbers, right? Red, positive, positive, red. So from negative pi over 2 to pi over 2. So that's one interval we have identified, right? From negative pi over 2 to pi over 2. So you identify this interval. Okay, so I'm going to mark that interval, negative pi over 2 to pi over 2. Okay, I'm going to use red to mark that piece. Okay, including the endpoints. Dot. So all of the points in between. So now that part is easy to identify, right? So how about this interval? We know it's at, this is pi over 2, so this is 3 pi over 2, right? So that's a 5 pi over 2, okay? So how do you identify that in the picture, right? So from pi over 2 to 3 pi over 2, this piece is out. This piece is out, right? This piece is out. But from 3 pi over 2, you go up, that's going to be 5 pi over 2. So that's how you identify the other interval, and so on and so forth, okay? So let's see if we can find a pattern. So the next interval here is going to be 3 pi over 2 to 5 pi over 2. Okay, so 3 pi over 2 5 pi over 2. So the next interval is identified. And the negative, right? So each one you have on the right side, you have another interval on the left-hand side. So let me show you. So this interval would be 3 pi over 2 over to 5 pi over 2. Okay, and the other side, right here, okay, the other side, and these will be negative, right? The smaller number on the left, larger number on the right. And this interval will also be over here, so I'm going to mark it right there. Okay, so I'm going to mark that. There. So we're gonna have we're gonna see patterns, right? So what pattern have we seen? What pattern have we seen? What pattern have we seen? The width of each interval is pi, right? The width of each interval is pi. So let's see if we can find a pattern. Okay. I would use 2k minus 1 pi over 2, 2k plus 1 pi over 2. Okay, and the difference is a pi indeed. So now it certainly works in this case, right? If k equals to 0, right? If k equals to 0. So in this case, k equals 0, that pattern works. I'm going to take the same pattern and move it over here to see if k works, if it works for k equals to 1. Okay, if k equals to 1, and that's going to be 2 times 1. That's going to be pi over 2. We need a 3 pi over 2. So how about we have, so this pattern doesn't work. So this will be 3 pi over 2. So how about this plus 3, right? If this is plus 1, whoops. I'm trying different patterns, and I also invite you to try it with me. Okay, so in this case, of course, we're going to use the same pattern, but in this case, we're going to choose k equals to -1, right? UK equals to -1. 2 times -1 is -2. -2 plus 1 is -1. K equals to -1. And this is going to be pi over 2. So it works here. And over here, we're going to try if k equals to 1. Okay. If k equals to 1, 2 times 1, that's 3 pi. 5 pi, it works for here. But how about this pattern? okay, what should be K? We're going to make it K equals to -2, right? -2. But this way, when K equals to 0, it wouldn't do it. It wouldn't do it. So when we specify the K, it certainly worked for this case, right? This will be -5. This is going to be -2, -4. Doesn't seem to work. -4 plus 3. That's a -4 plus 3. That's -1. So this pattern wouldn't work, right? This pattern wouldn't work. I think we all have to think about a better pattern, but at least we find the interval. Okay, so we leave the pattern for our thoughts. Okay, so let's think about it. Okay, so these patterns sometimes is not easy to figure out, but if it doesn't, no big deal. We already see a kind of pattern, right? We already see a kind of pattern. If we want to tell you, if we ask you what will be the next interval, the next interval is going to be, you can see from the pattern here, right? This is pi/2. This is 3pi/2. So next one would be, you can still figure out the next one will be 7pi/2. Okay, so 7pi/2. Okay, to 9pi/2. So we have a patterned answer already. It cannot be. We haven't found the formula. We haven't found the formula. And the other one on this side would be the negative, right? So this just may put the smaller one on the right, a smaller number on the left and larger number on the right. So we still have the answer. It's just we haven't found a formula to fit all. Okay, so let us think about that pattern that we can find. Okay, so solution to this question will be in the middle here and on the right side, and we can keep going. Okay, the next one will be 7pi/2, 9pi/4 over 2. And so let's put an answer to it. Okay, so solutions, you can present it this way. You basically present the pattern to the reader. Whoops. You basically present the pattern to the reader, right? So you let the reader observe the pattern. That interval, which is union, right? And union, and union, etc., etc. Okay, you can put a union here. And I think I'm sure the reader can recognize the pattern, okay, in both sides, right? They're all odd numbers. So we have the proper answer. It's just, we haven't found the formula yet. I think the formula can be found, I believe, okay? If you just try it, okay? I'm going to try it too. As I'm thinking, I think the pattern lies between these two. This quantity plus pi to get the next number, and this number plus pi to get the next number. Okay, so I'm going to give you a proposed solution. I'm proposing this, okay? So this answer I'm going to put it here plus k pi. Wait. Minus k pi plus k pi. I want you to try this. Okay. Wait. Plus k pi. So if I add, if k equals to, if k equals 0, we got the one in the middle. Right? If k equals 0, we got the one in the middle. You see, I haven't given up. If minus pi, that's minus 3 pi over 2. And minus 2. I'm not sure anymore. How about you guys give it a try? You come back to tell me if it works. Oh, okay. We can put it this way, right? Minus 2k pi minus k pi. So we give it as a pattern as 3, okay? If k equals to 0, if k equals to minus 2k pi, this is negative 5 pi, minus k pi, if k equals to 1, I think I'm going to give up for now for this lecture, okay? It probably takes too much time. I need some quiet moment to work on this myself, okay? There's no need to struggle over this in taking your class time. But still, I want you to think about it. Okay, we haven't found the formula. We did find the solution with the proper pattern. So let's look at another example. Let's look at another example. And this one, I would take example number 4. And this one, excuse me, is the question in your homework as number 4. Okay, minus 1 larger than 0. And of course, solve for x. Solve for x. Okay. Well, if we solve it the normal way, right? We will add in the 1 on both sides. And we take absolute value, we take square root. We take the square root, right? Square root of 1 is 1, right? Square root of 1 is 1. So this equals to 1. And the other side is absolute value is greater than 1. Do we have a solution? Do we have a solution? Knowing that the absolute value of sine x is always less than or equals to 1 for any real number, x. Therefore, what do we say? No solution, because that's the reason. That's the reason. Right? You can see we can use the previous techniques, but oftentimes we also have to take into consideration the specific properties of the involved function. And in this case, there's no solution. There's no solution. Okay. We have numerous examples of this kind. Let's look at some that require some factoring. Okay, example number 5. Okay, this is solved for x. This is number 5. Okay, we have 2 times sine 2x minus cosine x. 2 times sine 2x minus cosine x larger than 0. Right, 2 times sine x minus cosine x larger than 0. It's a little bit difficult, right? It's a little bit difficult to tell, right? So we're gonna do some algebraic manipulation, right? Sine 2x equals to 2 times sine x times cosine x, right? And we can factor out the cosine x, right? So we left with 4 times sine x minus 1, and we want this to be positive. Okay, and then what do we do? Shall we do some sign analysis? Well, these sign analysis is pretty difficult because the domain is all real numbers. Right? So we want to identify the points where the function changes sign. Okay, when does the cosine x changes sign? When does sine x changes sign? When does a 4 times sine x minus 1 changes sign? Right? So we need to do that. So we're gonna identify points where the sign change, the sign, the function may change signs. What does it mean change sign? Change sign between positive to negative and negative to positive, right? We're pretty familiar with the cosine function, right? Cosine function, you can see the sign change takes place. So when does the cosine x equal to 0? Right? Cosine x equals 0. So when does the cosine x equal to 0? If we bring our unit circle, that could help us to identify when cosine x changes sign, right? When? Between at a pi over 2, right? You see the red number to the when the angle is less than pi over 2 here, from here, right? It's a positive, negative, and 3 pi over 2, negative, positive, right? So these what we mean by changing sign. So x change sign at what? At odd number multiples of pi over 2. This is the domain of tangent, right? Tangent equals sine over cosine. So this is the domain of tangent is x cannot be equal to, right? So this is similar to, cosine x, cosine x equal to 0 or not equal to 0, which is for tangent, right? That's a domain for tangent. Cosine x, so let's graph the curve. And you know what I meant. So cosine x we are very familiar with this function. Or you can use a decimals picture. So where it changes sign? Where did it change sign? Negative pi over 2 negative 3 pi over 2, negative 5 pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, right? So these are the numbers where it changes sign. Why? Because here it's negative. Now it's a positive, right? Change to negative to positive. So this is what we meant by sign changing and where it changes sign at these dots, at these places. Okay, and these places are expressed by x equals 2k plus 1 pi times pi over 2. Odd number multiples of pi over 2. So that's where the sign changes takes place. Okay, sign changes takes place. All right, so that's clear. Let's see when does the other factor changes sign. When does the other number changes sign? Okay, we make it equal to 0, right? And sine x equals to 1/4. Right, sine x equals 1/4. How do we solve this equation? How do we solve this equation? How do we solve this equation? Well, if you look at you want sine x equals 1/4, right? You want to identify all of those solutions. How do we identify all of those solutions? Well, let's draw the rectangular system. We've done something similar before, right? It may not be the same number. According to our definition, so here, so let's set up the rectangular system correctly. Okay, set it up nicely. Oops, here. Okay, sine x equals to 1/4. 1/4 means what? The definition of sine is y over r, right? Or the blue over r, right? The blue over r. The blue is 1, right? So if we know that the radius, the r is 1, the r is 4, blue is 1. So we just need to find the red, right? So the blue is 1. Oops, okay. The blue is 1. And the r is 4. Okay, just approximately. I will give you a precise drawing. So this is a 4. And the blue is 1, right? And what is the red? That's right, this is what we did before, right? Something similar. We use Pythagorean theorem, right? We use Pythagorean theorem. So the red is equals to the square root of 4 squared minus 1 squared. Right? Minus 1 squared. So that equals to square root of 15. So the red is square root of 15. Okay? So root 15 equals to that. That's the red. Okay? And then what? We can compose our solution because there's another terminal. There's another terminal. The other terminal is on the other side. Okay, so on the other side, there's a red, there's a blue, there's a blue, and there's the green. there's a hypotenuse, right? For 1 and negative root 15, right? So for this situation, for cosine, for sine x equals to 1/4, we have 2 terminals corresponds to it. So how do we represent these angles? And this angle, okay, we're gonna call it theta, can be represented using, we can use theta. We can use theta equals to arc sine 1/4. How about the other terminal? The other terminal would be this, right? So that's going to be pi minus theta. That will be pi minus theta. So the solutions are, so let's see, what are the solutions? The solutions would be theta plus 2k pi or pi minus theta, which is the other terminal, plus 2k pi. All right, it gets a little bit complicated, right? Just to determine the sign change. So now we have found these numbers of sign change. So let me draw this for you to give you some time to digest this. I'm going to draw the proper picture. Okay, draw the proper picture. And these things are, okay, it's root 15, okay, 1, and this will be our hypotenuse. Okay, we got 2 hypotenuse. 2 hypotenuse. And the 2 blue. The 2 blue. The 2 blues and the 2 red. Blue and red. Okay, so what is the angle? The angle theta is right here. This is the angle theta. Okay, this is the angle theta. So we have 2 solutions, 2 forms of solution. We have many, many solutions, okay? And the k, of course, are integers. So these are the places that 4 times sine x minus 1 changes sign. Let's look at that function. Okay, so I'm going to draw this picture. See, the analysis of these pictures can be a little bit more interesting, isn't it? So we have over here. Oh, huh. There. Hold on. Okay. There we go. I think I put the wrong number in the wrong place. Something like that. How do we identify? We just identify the numbers where sign changes takes place, right? This number This place is a theta. Okay, so this much is theta. That's arc sine 1/4. This is arc sine 1/4. The arc length, this is arc length. And plus k plus 2k pi. Plus 2k pi, right? Because these are the solutions that where sign changes takes place, right? These are the solutions where okay, hold on. Let me bring both pictures together. Okay, let me bring both pictures together. We have good use for them. Oh, I can only copy one at a time. Okay, I'm going to copy one at a time. Okay, this is the cosine picture. And this is the other picture. You can see when we compare them with a comparative scale, right? We have the picture right here. So this is becomes very important that we actually know the meaning, right? This is a cosine, and this is a 4 times sine minus 1. We have a cosine here for this piece, and this piece is 4 times sine minus 1. Okay, so the second piece. Oh, wait. How did I get that? Huh, I don't know. I have no idea. Okay. This is the 4 times. This piece is a 4 times sine x minus 1. Okay. So we're going to bring back the cosine later. Okay. To understand this picture, right? We know there's a theta plus 2k pi. That's the solution, right? Solution for it equals to 0, right? So we know x equals to this piece or that piece, right? Or we can write it this way. So for that piece equal to 0, the solution is such. X equals to right here. Okay, I put them in the familiar forms. So theta, of course, we know what theta is. Pi minus theta, right? K is integer. And we also have a theta. Theta is this piece. Okay, so everything is well specified. Theta. Theta is is an angle, right? And what is it? What is it? This quantity, this place is theta. Okay, plus 2k pi, plus 2k pi. So this place plus 2k pi, so we get to the next place. Oops. Bring this over here. Okay, so plus 2 pi, we get to here. How about pi minus theta? Okay, pi minus theta. Pi minus theta. Okay, pi minus theta. This quantity is right here. Okay, and plus 2k pi, so this whole thing is going to be over here. So this point, excuse me, so let me see, let me show you. From this piece to that piece, the difference is 2 pi, 2k pi, right? 2 pi. And from this place to the next place, that's 2 pi. That's 2 pi. Okay? Now, let me remove some stuff. This will be clearer, right? Theta plus 2 pi. This is theta plus 2 pi. Okay, so let me change the color. And theta plus a pi minus theta is this piece. Okay, pi minus theta plus 2 pi, okay, is this piece. And between the stars, the difference is 2 pi. If we minus 2 pi, it's going to be here. This is heart. Okay. So between these two hearts, that difference is 2 pi. And between the star, between these two stars, that's 2 pi. Between these two stars are 2 pi. Is that clear? Okay, so let me show it again. Okay. Between this piece and that piece, the difference is 2 pi. The big difference is 2 pi. Okay, and there's another heart. There's another heart, which is right here. Okay, and that difference is 2 pi. That difference is 2 pi. And all of these hearts are expressed right here. Okay, so now let's look at the stars. Star, star, star. Okay, between the stars and that difference is 2 pi. The difference is 2 pi. And they're expressed using this piece. Okay, so now we have the points clarified, right? We have the points clarified. But now we're still solving the inequalities, right? We're solving the inequalities. So what is that inequality, right? We need to bring the cosine back to our picture. And what we consider is the product. We look at this product. We want the product to be positive. Okay, so this is wanted. Okay, we want the product to be positive. Okay, wanted. So we're going to observe the product. The product. Oh, to be precise, the sign of the product. Okay, so now I'm going to make the picture just a little more manageable so you can see both pictures at the same time. We're observing the product. Sign change, right? We have identified these points. Take some simple part, for example. This is theta, right? This is theta. This piece is theta, right? So this piece is theta. Okay, and there's a pi minus theta, right? So we're going to observe from here to 2 pi. Okay, we just look at that part. So I'm going to make a couple points, marking certain points. So let's see, where's my theta? My theta is this piece, right? So I'm going to mark that point on my picture. Theta comma 0, I'm going to make a red dot, right? And the other point I'm going to mark is pi minus theta pi minus theta comma 0. So that's another red dot. Okay, right here. So now, if you look at the, okay, I'm going to give you the idea how to do it, right? So this play, just look at the crossing the 4, between 4 and 0 on the y-axis here. You can see on this piece, it's negative, right? This piece between 0 to the red dot, piece is negative, but this piece is a positive, right? And so negative times positive, that's going to be negative. So this piece is not solution. But from here to the next dot, right? We have the whole thing positive. But here, this is a pi over 2. This is pi over 2. Okay, this is a pi over 2. So this is, let me mark it. This is pi minus theta, right? And this piece is a pi over 2, right? So between theta to pi over 2, so if you look at this piece, right? If you look at this piece between theta to pi over 2, right? This piece is a positive and that piece is a positive. Positive times positive is what? Is a positive. So between 0 to pi over 2, not including pi over 2, because pi over 2 is a cosine, pi over 2 will be 0. So pi over 2 here, I'm going to have to make a circle. I'm going to have to make a circle. So that's how you identify solution. Pi over 2, comma 0, and this is going to be a circle. Theta need to be a circle too. Why? Because at theta, this piece is 0. So I'm going to make these 2 red dots circles. Circles. So now we have identified what solution from theta. Okay, there's a theta here. Sine 1/4, comma 0, and that is circle. So what I'm saying here, I hope you get, I hope you're patient enough to get my idea, is between theta to pi over 2. Okay, let me use red. Okay, between theta to pi over 2, not including theta to pi over 2, this piece. Okay, this is 4 sine x minus 1. So this piece, positive piece, and multiply this positive piece, that's positive. So I found one solution. That solution, I'm going to mark it, which is the red. Okay, so just be patient with me. And that is going to be arc sine 1/4, 0, pi over 2, comma 0. That interval is a solution. Oh, wait, I meant to have it being red. Okay, make it red, thick, and this end is a circle. Okay, be patient with me. So now circle. Oh, I want it to be red circle, right? Red circle. So on this interval, you can see the curve is positive from 4 times sine x minus 1. And this other piece is from theta to pi over 2. So let me make some adjustments so you can see the correspondence, which is, this is going to be a red circle. Red circle. Pi over 2. Okay, we found one piece of solution already. This one piece of solution is between theta to pi over 2. Theta to pi over 2. On this piece, you can see the curve is positive times positive. So positive times positive is a positive, right? So we got a piece of solution here. So the first interval is theta to pi over 2. This is how you identify solutions. It's not easy. It's not easy. And we keep going. We keep going. And from pi over 2 to here, you can see this whole thing is a positive, but this piece is a negative, right? So from here to there, this piece is a positive, but this piece is a negative. Positive times negative is negative, right? But this piece is a negative, and this piece is a negative, okay? So negative times negative is positive. So we see there's another piece from this number is, this point is pi minus theta. So there's a pi minus theta on this piece, on cosine curve, right? So pi minus theta okay? So there's a pi minus arc sine a quarter. And this point, there's a red circle. Okay, so these 2 points, that's a pi minus theta up to here, up to here. Okay, because this entire piece is negative, this piece is negative. So what is this point? This is pi over 2. This is 3 pi over 2. So 3 pi over 2. Okay, so you have to read this, right? So 3 pi over 2. But actually it gets to be interesting, but sometimes questions like this can get to this much of complication. You have to do little bit at a time. But the basic principle hasn't changed, right? This is a 3 pi over 2. So there's a 3 pi over 2 in that picture. Okay, there's a 3 pi over 2 in that picture. So I'm going to point it to you, right? So 3 pi over 2, comma 0, so that there's a red circle there, which is a circle. You see, between these two circles, the curve is negative. The curve is negative. Negative times negative is a positive. So we have identified another interval of solution. So that interval of solution would be, that's pi minus arc sine a quarter. Okay, and 3 pi over 2, 0, there's a line segment. And that piece of line segment, which is the red piece, is the solution over there. So we identified another piece of solution. Like that. But this time is negative times negative is positive. So another piece of solution, okay, the second interval of solution would be pi minus theta to 3 pi over 2. You can see how the graph will help us to identify that solution. So we can keep going. Okay, keep going. And then you can see this is a negative, right? And that's a positive. That's not going to take us very far. But you can see there's a point over here, right? And this is a positive. And this piece is in positive. So you're going to find this point. And this point is what? This point and that point is 2 pi, right? That difference is 2 pi. So theta, okay, plus 2 pi. Okay, theta plus 2 pi. So arc sine of a quarter plus 2 pi, comma 0, what that circle, boom, okay? So that point, starting from that point, and this same point, right, on this picture, right? So from here, you can see that's a positive curve. That's a positive output. So positive times positive is negative. So one does a change sign. Oh, it changes sign here. So what is this number? What is this number, right? So this is a cosine curve, right? So this is 0 pi over 2 pi, 3 pi over 2, 2 pi. So this is 5 pi over 2. Okay, so this is up to 5 pi over 2. Five pi over 2, comma 0, and that's a circle. There. On this picture, you have a similar situation, and you have a red circle. And between these 2 points, we have a positive times positive, which is going to be positive, right? So we still use the mathematical principles. So let me mark that interval. Right, let me mark that interval. That interval is arc sine 1 over 1/4 plus 2 pi, comma 0 to 5 pi over 2, comma 0. And there's a line segment thick. That piece right there. And we have that piece over there. So this piece is a positive times positive equals to positive. Okay, so we continue this process. Okay, we continue this process. On this side, you do the same thing. On this other side, okay, you're gonna do the same thing. Okay, so I hope you get the hang of it. Are you going to ever encounter these kind of issues? Yeah, it's very possible. It's very likely. It's very likely you're going to encounter such issues. And, but you can see mathematical principles is being used. Okay, mathematical principle is being used. You just have to be able to identify all of these points. For example, this is theta plus 2 pi, and so on and so forth. So here, this theta minus 2 pi is going to fall over here, right? And you can determine this point. That point is going to be plus 2 pi. You're going to get over here, right? So these two is 2 pi. I'm sorry, between this piece and that piece, that's 2 pi. So this piece and that piece is 2 pi. So let's just do a 1 or 2 cases on the left side, right? We want a positive. What do we want? We wanted a positive product. So positive product we got from positive times positive, negative is negative, right? So here, this piece is negative, this piece is positive. So if there's nothing it's going to be produced. But from this point, right, this piece is negative and this piece is negative, right? So negative times negative is a positive. So we need to identify this point. This point is negative 2 pi over, negative pi over 2. Okay, so I'm going to identify this negative pi over 2. It's pretty, you know, I would say it's hard work. It takes a lot of patience. So negative pi over 2. So you're going to identify negative pi over 2 over here. Okay, so let me draw a vertical line, right? So this is a negative pi over 2, right? And there's another piece here. And this piece is a negative times negative. That's going to be positive. So you just need to identify these points. And since this is the cosine curve, we have identified that's a negative pi over 2. So we're going to identify the same point in this picture. Okay, negative pi over 2. Okay, and they're going to be red circle. Okay, so these 2 points are identified. And here, this place and that place is 2 pi. And what is this? This is a pi minus theta. So this point is pi minus theta minus 2 pi. Okay, this is a pi minus theta. This is pi minus, this is pi minus theta. Pi minus theta minus 2 pi we get here. Okay. Well, I hope you guys have the patience to listen to me. So pi minus theta, arcsine of quarter. We have to minus a 2 pi to get to this point. Okay, we let the computer does the work. And there we go. Right, you see there? You see there's a circle there? And you also have to draw the same circle over here. Okay, so let me delete that. Okay, so now we just have to identify the same point on the other picture. Pretty soon you get the hang of it. You see, these 2 circles are identified. They are the same point. You can see I draw the picture on the same scale. Everything is, you know, they're all lined up. But this point is negative pi over 2. And this point is pi minus theta minus 2 pi. Okay. So now this interval is going to be solution as well. Okay. So I'm going to mark those interval. Negative pi over 2, 0, line, thick. There, I'm right. Okay, and on this picture, we're gonna do the same thing. The red, make it thick. So this way, you're gonna do piece by piece to find the solutions, But the general principle has not changed, So let's put the solutions. I forgot to write down this solution, right? This solution would be, this is the theta pi minus theta. This is gonna be theta plus 2 pi, right? And then that's 5 pi over 3, 5 pi over 2, 5 pi over 2. Oops, 5 pi over 2, right? So that interval is 5 pi over 2. On this side, we also have an interval. Okay, what would that be? It's pi minus theta minus 2 pi. Okay, on the other side is a negative pi over 2. So that's one interval, that's another interval, solutions, that interval, solutions. And you can keep identifying those solutions, right? So in this interval, it's a negative times negative, okay? And this piece is negative, that piece is positive, so it's not gonna make it. But here, you get a positive times positive. So you're gonna start from here. Okay, so let's just do one more. I think it's about time that you're tired. I'm sure you're probably already tired. Okay, there. So let's identify which point, because this is a cosine curve, right? So what would this point be? It's a negative 3 pi over 2. Am I right? So this is negative pi over 2. This is negative 3 pi over 2. So I'm going to mark that point with a circle. 3 pi over 2, comma 0. I'm just using that software, right? So negative 3 pi over 2. And I'm going to mark the same point on the next picture. Negative 3 pi over 2. Circle. You see? So we get 2 circles identified. This is a negative 3 pi over 2. And on this piece, that's positive, and on that piece is a positive. But this is positive for longer. And this turned color at here, so what is this number? And this number is theta minus 2 pi right here, okay, this place. Okay, you can see this place and that place, that difference is 2 pi. So that's the theta minus 2 pi, okay? Theta is arc sine 1/4 minus 2 pi. So that's circle, okay? Oops, minus 2 pi, I'm missing something. Minus 2 pi, right there, you see? And on the same place, I'm going to have that red circle as well. So between these 2 circles, that piece is positive, that piece is positive, so positive times positive is positive. So I just have to mark the entire interval, okay? Okay, so theta, and then And the other end is negative 3 pi over 2, right? Negative 3 pi over 2, comma 0, line thick. Right there, you see that solution on the same piece. On the same piece. Yeah, so positive time positive. So you can continue this process. So what is the last interval have we found? The last interval we have found is theta minus 2 pi, okay? Negative 3 pi over 2. So all of these interval union, okay? I'm not gonna try to find a pattern anymore. If you want to, you can. It's gonna take some time. Okay, so these are solutions. And these solutions, you can keep going. Okay, keep going. Keep going. Okay, in the process, you can identify certain patterns, right? So you can see this theta minus 2 pi, theta minus 2 pi, and then the next one will have certain pattern. So these patterns will keep going. So you have shown a pattern, but it's kind of hard to make a formula out of it. So just you know, I'm content with this kind of solution. We apply the principle number 6. We still apply the principle number 6. It's just how to, right? It's certainly there's an added complication. Then you say, well, can I do it? This looks more complicated, right? This looks hard. So could we just graph this picture entirely? Sure, let's try that. Why not? If I graph this picture entirely, that's what you get. Okay, but the dilemma we have, okay, the hard part we get. So what is hard here is this. Is how to identify these points. How do we identify these points? Okay, so I'm gonna take this picture. I'm gonna take this picture. Okay. And bring our other 2 pictures here. I'm gonna have you decide. And for this picture, I'm gonna change it to the same scale. -10, +10. And I'm not gonna change anything else. Okay, you still need to identify. You can see, obviously our solutions are correct, right? Because this is the, hold on. Okay, I want to show all 3 pictures to you. I'm going to show all 3 pictures to you. Okay. The hard part is to identify the points, right? So you can see this is theta, right? So let me bring the interval we have found. Sure, I'm certain about our solution. Our solution is correct. Okay. And our solution here, this is our solution, okay? This is our solution. I'm going to make it just a little smaller for you to identify, for you to see, right? So this is the whole of the curve, right? And this is just this is the part of it. This is a part of it, and this is the cosine curve. They are completely comparable with the same scale, right? From -10 to +10. You can see that our answer is right because this piece is a positive, right? And that piece is a positive, that piece is a positive, that piece is a positive. Visually, it's very easy to identify. We just need the positive piece, right? And what we need is just these pieces, not including the endpoints. These are our solutions. And we have identified that with our hard work. But the question is, in order to identify the left side, the right side of each interval, we will have to go, we still have to identify these points. We still need to identify these points, which is, this is a theta, right? And this is pi/2, right? This is pi minus theta. This is 3 pi/2 and so on and so forth. You guys know what I meant, right? So you still have to identify these points. So the way we did it, right? Even though it looks long, it looks pretty complicated, it allows us to identify those points easily. Even when you work with this, you still have to face the same issue. You may still have to work with these individual terms in the individual graph to identify these points that marked by the circles, right? To identify those points is the major task. Visual effect, no problem. It's just identify those values. You have to resort to the algebraic analysis. Okay, so without further ado, I think this lecture is long enough. I hope you have the patience to watch it from beginning to end. Otherwise, come back to watch it again, because these probably represented the most complicated of solving inequalities of all time. And I will have another lesson to talk about solving inequalities and hopefully give you some ideas to see the simplicity. On the other hand, you will also see the complexity of solving inequalities, okay? It can be hard. And but the principle to follow is simple and easy, which is principle number 6, okay? So without further ado, thank you for watching. Until next time.